So you simply add this term for every system.
How does that then capture the statistics?
By this. Yeah, it takes a little while to sort of realize. At first it looks like a cartoon, but there's something actually very sophisticated going on here. So again, right, so the photons coming in, the Doppler shift, and therefore they must have more energy down here than up here, right?
And you just pick one that's linear?
No. Then you simply forget about this current because this current's equal to that current.
Oh, okay.
Then you just calculate that. No temperature gradient now in your problem. It's sort of cheating, but a very clever way to sort of step aside from the problem, and then you just put it into linear response. So in a magnetic field, you get a lot of terms, but and this is not the place, or I'm not the right guy to talk about that. But anyway, I'll just tell you about how these ideas evolve. All right, so these are sort of the quantum Hall era, and then now for Berry curvature effects in thermal experiments, Murakami has revived this experiment. Revived this approach. All right, so another idea by Luttinger, which again started even earlier, right? This is 54 now, right? So this is 10 years before the last thing that I talked about, is this notion of Berry curvature, right? So what is the Berry curvature? Well, all of you know what this is right now, but let me sort of give you a ground zero intro to this. So the notion of anomalous Hall effect in a ferromagnet had been known for like, maybe 50 years by 54. So I think Erwin Hall discovered it in the late 1900s, 1800s. And it was always a mystery, where did this anomalous contribution come from?
If I have a temperature gradient, that does not really depend on the frame, but it seems to me that
on the frame,
meaning if I
reference frame, you mean?
Yes. If I do the calculation in a moving reference frame, wouldn't that mess up the calculation?
No, this is all in the lab frame. Where the
yeah, but my question is, if I go into a moving frame, then this.
when you go to the gravity problem.
Yeah. Then this gravitational time goes away.
Yeah. It's that brings up all kinds of interesting notions that maybe I'll talk of it very briefly at the end. So this whole notion of gravity coupling to thermal conductivity has recently become very interesting because gravity and condensed matter seem to be overlapping. I'll mention this sort of frame dragging effect, which so far no experiments have made contact with. Well, I'll come back to it in the end. Yeah. Okay, so in 54, Luttinger and couplers just did quantum mechanical transport. Just did an honest calculation of the response of the electron gas to a magnetic field, and applied electric field. And the calculation kept turning up this quantity, which today we will call A. They call it J, but anyway, this is A. And A is nothing but I don't have it here. Anyway, it's the vector potential that corresponds to the Berry phase, right? So if you go around a closed loop in K space, and there exists a vector potential in K space, now not in real space. So it's not the Maxwell vector potential. This is the Berry vector potential. If the closed loop experiences a vector potential, then the particle going around the loop acquires a phase, right? We will call that the Berry phase, right? So that's A. And Luttinger discovered that in couplers. And then this led to a lot of confusion. Adams and Blount thought of it as the interstitial coordinate. And actually this has become a very fruitful way of thinking about it. When you do condensed matter physics, you have Voinier states on the sites, and you never ask what happens to the electron when it's in between sites, right? You don't care because it doesn't even enter into your picture, right? And that's provided you stay in the lowest band. the lowest energy band, right? So if you have a wave packet that you accelerate and it moves around, the assumption that it doesn't make virtual transitions to higher bands means that you don't care what happens in between, you only worry about the lattice sites. Right? So you have thrown away a lot of information. And normally it doesn't hurt you except when Berry curvature appears. So the Berry curvature is nature's way of telling you that you've thrown away a lot of stuff. So that's what the Berry curvature is. So if you propose that there is an interstitial site A, and you go through and do some very simple quantum mechanics, calculate the commutation relation, you will pick up, for example, if you commute x and x, you don't get 0 as an ordinary free space quantum mechanics. You get the Berry curvature, which is the gradient in k space of A, of this quantity. Oh, I did write it down. So A is the inner product of the periodic part of the Schrodinger wave function with the momentum operator. It's sort of the overlap between the periodic part. And this quantity, so this reminds you of particle motion in a magnetic field, right? If you take 2D gas and do the commutator, you will pick up L squared, the magnetic length squared, right, in a magnetic field. That's the behavior of electrons in a magnetic field. But there was no magnetic field in this problem. So you conclude that there actually is a fictitious magnetic field corresponding to the Berry curvature, which has dimensions of area, right, say from here, a physical area. And it acts on a wave packet. Right? So why don't we see it? Why don't we see it in aluminum and gold and whatever, right? You measure current, it always wants to turn sideways because of this fictitious magnetic field. Well, one can show that if you have time reversal symmetry and inversion symmetry working together, omega is always 0. It's suppressed by symmetry. But, it's like charge, We all live in a universe that is more or less neutral, but there's almost perfect cancellation between charges, right? Positive and negative. But when cancellation is imperfect, when it deviates in one part in 10 to the 20, you see the effect right away. So there's this very powerful force that is cancelled almost exactly. And a lot of the interesting effects in Maxwell physics comes from deviation of cancellation. So a similar situation is here. If you have a lattice that has inversion and time reversal symmetry, omega is hidden. But it's not absent, it's always lurking there. And the moment you make it, you break these symmetries, it appears with full force. And its appearance, suggested by Luttinger and couplers, was what causes this new contribution to the Hall effect. So the anomalous Hall effect, 50-year-old mystery, received a very elegant explanation in terms of Berry curvature. At the time, of course, he didn't know about Berry curvature. And Luttinger himself was very puzzled by this and wrote a few papers, but he was attacked by many of the people interested in ferromagnetic systems. And basically in '64, he dropped the problem. He wrote his last paper and walked away from it, and convinced that he was right because he had done the calculation, from every which way. And now today, of course, this is called the intrinsic anomalous Hall effect. So this is probably the earliest appearance of Berry curvature, Berry phase effect in condensed matter. I can't think of an earlier example. This really is it. And it's spectacular, right? Because the Hall effect in a ferromagnet can be 10 to 50 times larger than the Hall effect from the Lorentz force that you apply. So this is what I mean, right? So the Berry curvature, when it appears, it acts as if it's a magnetic field in K space of a few hundred Tesla. And in the lab, you'd be happy if you could apply 10 Tesla. So it's just lurking there, waiting to appear. You break the symmetry like time reversal, it will appear. Okay, so this is the beginning of Berry curvature. Oops, did I skip a slide? Oh, okay. All right. So Murakami pointed out that the earlier paper had neglected the gravity effect from Luttinger's other effect. And he presented two, so he was going up against his previous boss. He had to be very careful. So this especially, never mind. He had to make sure that he solved the problem in 2 or 3 ways to convince himself that he was right. So let me give you the easier way, which is based on semi-classical notion. And I think I can explain this. The harder way, which is using Kubo approach, is let me just direct you to these 2 papers. So you start off with so I forgot to tell you that the primary results of this Berry curvature is to change the equations of motion, right? So I forgot to tell you that, so let me do it here. So the big change, right, when you open up Ashcroft and Mermin, you find that the velocity in the semi-classical limit of a wave packet is the gradient in k space of the energy dispersion, right? And that's it. And the other one is involving k dot, which in this case, charge is 0. Okay, that doesn't appear. But anyway, here the Berry curvature adds a velocity. This is called the anomalous velocity. In my mind, this should be called the Luttinger velocity. It adds this velocity to the group velocity that we get. So all future condensed matter textbooks, even at the level of Cattell, will have this term, hopefully. And once you put it in there and you go through all the calculations of semi-classical transport, Hall effect, and so on, everything changes. You get new terms, and working them out is something that my group and others have been focusing on for the last few years. Okay, so you have a new term, which is k dot cross into the Berry curvature. In this context, k dot is the acceleration, right? But there's no charge. However, there is a potential, and this potential is simply the wall potential that prevents the magnons from leaking out. Right? We're talking about magnons here. So here's a sketch. When the wave packet of magnons comes to the edge of the sample, it can't leave because there's a very steep wall, right? So this is called U, big U, and its gradient, which is obviously the force, right, acts to accelerate the wave packet in this manner. But now you put this acceleration back to here, you find that it's a Hall direction, right? Because this is a group velocity, and anyway, this will become clear in a second. And the vector potential A, which I introduced earlier, sorry, this is so disorganized. So this vector potential, if you now operate with a curl, right, operate on this with a curl in k space, you will get this expression, right? So this is simply the curl of the gradient term in k acting on both the bra and the cap with the cross product in between. Okay, so Murakami proposed that in these spin-on systems, the existence of the wall will create an edge current. So this is an edge current for the wave packet, and it's in the semi-classical limit, it's just the magnetization current, right? So you know from undergraduate E&M that whenever you have magnetization, the curl of M, right, gives you a magnetization current which goes around the surface. So this is the same thing. Right? Now you put this in the temperature gradient. So this side is warmer, and this side is cooler, right? So you notice then that there will be a bigger population for this edge mode than the cooler side, right? And therefore, you apply a gradient in the y direction, you get a net flow of heat, right, in the x direction. That is the source of the thermal Hall effect, according to Murakami. And you see that you need a Berry curvature to get that. So how does the Berry curvature appear? Well, okay, take the cross product. So this is gradient U for the wave packet sitting on the left wall. Gradient U points to your right, right? Because it wants to push the wave packet back into the bulk. And the Berry curvature points up because it locks to the external field. It locks to the external field, and therefore the cross products of the force with the omega leads to a velocity that goes into the screen. That is the edge current. So a wave packet, as soon as it drifts close to the wall, will then just get pushed around by the Berry curvature. Okay, and again, so this is the key point, right? If you apply a gradient, the warmer leg will have a larger population of magnons, and therefore you'll carry proportionally more heat than the back flowing edge, which is the cooler part. So you add these two together to get the Hall current, and then you Taylor expand as usual, because it's a very weak gradient. And you see that the correction, the net difference is the derivative of the current in each arm, each segment, right? So the current then is simply the integral of the Bose distribution over the Berry curvature. So kappa xy is directly measuring the Berry curvature without, except that it's being modified by energy distribution, temperature, and so on. Okay, we're going to collect all this integral into a factor called C2. And this has all the uninteresting, Bose distribution and energy factors. And then you can write, finally, you can do the same thing for the particle current and the energy flux. This is the energy current, right? But this is not what you measure in the thermal conductivity. So this is a common misconception. You're not measuring an energy current when you perform thermal conductivity. You're measuring the difference between the energy current and the particle current, right? Because you're always reckoning your energy flow with respect to the chemical potential. So you add these two together in this form, and you get the thermal conductivity in response, right? But now we are focusing on the Hall effect. So you put a gradient this way, and you get a current flowing to the right. What's the sign? Well, this is a bit tricky because there's no charge. There's no right-hand rule or Lorentz force to help you with the sign. So it's a little bit, I better speed up. This is let me just go on. Anyway, so you see that the kappa xy is the Berry curvature itself, except for this kernel, which has all these uninteresting band structure effects and occupation effects.
Question. The force equation R dot is equal to
this equation?
Yes. Looks like that the Berry curvature term, it only acts in the edge of the physical space.
No, here there's no boundary condition yet. This is for everywhere.
No, but the wall potential is presumably...
For this problem, yeah, for this problem.
On the wall, right?
Yeah, for this problem, yeah. That's right.
Yes. So, my question is, but can we neglect the effect of the Berry curvature in the bulk completely? When doing the calculation?
Yeah, because there's no potential in this model.
So no Berry potential inside?
No, there's Berry potential, Berry curvature.
Yes.
But there's no U, no gradient of U.
Right, but how about effects coming from, let's say, the
impurity and so on.
impurity?
Sure, yeah, then there will be, yeah. There will be, yeah.
And if you want to significantly modify your...
No, that wouldn't give rise to this Hall effect. It could, there's something called skew scattering, but that's, yeah, it could in a minor way, yeah. Okay, now they repeated this in linear response, and I won't go through it except to point out the nature of their final result, which is sort of interesting. They found that if you do this seriously using Luttinger's gravitational potential, it breaks up into two parts, S and M. S is the purely Kubo term that Nagaosa and Lee had obtained. But now you have this essential magnetization current. And when you add them, so I've